Okay, yeah, let's start. Welcome everyone to the first session, free TypeScript course for developers. I'm Javier, the co-founder of the ICP.Hub North America. We are trying to create awareness about the Internet computer and bring developers and projects to the Internet computer blockchain. This course is related with Azle Book. Azle Book is created by Demergent Labs, and we have here the founder and the CEO, Jordan Last. Demergent Labs, they are accelerating also the adoption of Web3, the Internet computer, and the sustainable open source. The course, Azle course, is divided in 5 sessions. Today we have the first one. We will cover the chapters from 1 to 9, covering crucial topics: installation, hello world, deployment, and also an overview of the Internet computer canister. Yes, over to you, Jordan. I know you introduced yourself yesterday, but you want to do it again, and yeah, we can start. Thank you so much.
Yep. Hey, everybody. It's Jordan. I'm from Demergent Labs, CEO there. We're the small team that's building the TypeScript and JavaScript environments on the internet computer. So yeah, last time we had a really nice, fun introduction to blockchains and decentralized computing in general, and kind of the trade-offs between the internet computer and other systems. So today we are actually going to start some actual programming with the internet computer, and we will show you how to get Azle set up. So let's just jump right in. I need to be able to share my screen.
Oh yeah, give me 1 second, please.
Yep.
Yeah, I think you can.
Okay. And yeah, feel free at any time to just pause me and ask any questions that you want. And that's probably the best way to do it. And there aren't that many people, so we should be able to do that. So yeah, first things first. This is the repo, github.com/demergentlabs/Azle, right? Azle is the TypeScript CDK for the internet computer. Azle is basically the TypeScript or the JavaScript environment for the internet computer. At least it's the one that we're building, and the only one that I know of. I just want to show you a couple things in the repo first. First, a disclaimer: Azle is beta software, so it's new. It may have unknown security vulnerabilities. I don't know if we reviewed any of this before, but I'll just go over it again just in case. So just keep in mind, it is beta software. We're working very hard to move it beyond beta, but for now it is in beta. And yeah, we have lots of things planned to make Azle super rock solid and super amazing. And it's, I think, pretty good right now for what it is. But just keep that in mind. And then basically all the main documentation will be here in the Azle book. Azle book can be found here at demergentlabs.github.io/Azle. And real quick before we leave the repo, I just want to show you the examples directory. This examples directory has something like 60 examples covering all kinds of the just all the functionality and all the APIs that Azle has available to you. So if you ever need to know how to do something, hopefully there is an example at least showing you the basics of what's going on, at least for the core APIs. So yeah, keep that in mind. And basically we'll jump into the book now. We tried to make this book like an in-depth guide. The book's not entirely finished, so things get sparser near the end, but definitely for getting you jump started, I think it is a very, very, very good resource. And I think you'll find that learning Azle is really not that complicated. If you already know JavaScript or TypeScript, I mean, you're just learning a few new concepts to get JavaScript and TypeScript to work in the internet computer context. So chapter 1 is just this title page with the license. Chapter 2, I think, is quite interesting. Chapter 10, I think we'll go into this just a little bit. In the last episode or whatever, we did talk about some of the trade-offs and benefits of the internet computer. Chapter 2 is all about these, right? It talks about the benefits and drawbacks of both Azle and of the Internet Computer. And we tried to boil it down to like the very core things. And if I could boil it down, then at least according to this documentation, I've thought a lot about this since, but basically if we boil it down, the main benefits can be broken down into ownership, security, and developer experience. So what's very interesting about the Internet Computer, right? It lets groups own entire applications, front end to back end. You can have a group actually own it. You don't have to have one person or one company with an account on the cloud platform. You can have multiple people with key pairs and they can all own it together. You can also make applications that are owned by nobody, like there is no owner, which is quite interesting. You could possibly create permanent APIs. Like imagine a web API that will always be available and will always have a certain interface as long as you pay, or you or someone else can pay to keep it up. That it's not going to be revoked or just take it down for I guess silly reasons. If you need credible neutrality, having a group own something or having no owner is a way to make a neutral platform, right? Imagine an app store. The app stores that we have, right? We have an intermediary, and then we have a bunch of apps that want to use the app store to kind of coordinate their activities with their users. Well, that central entity might not have the best interests of the apps in mind, and vice versa. So it might make sense for the apps to get together and create a neutral platform that is not going to try to exploit them. So just as an idea, and then reduce platform risk, right? If a group owns something or if nobody owns the app, then you're going to probably hopefully reduce the risk of a large company just deciding, for political or religious or business reasons, just shutting it out, right? So we go into all of these things here in a little bit more detail. And then there's the security, which is very interesting. The Internet Computer gives you built-in replicated computation. And I'm just kind of glossing over this because we did talk a lot about it in the last episode. But we have built-in replication. We have built-in authentication. There's public-private key pair authentication. At least that very simple mechanism built in. You really don't need to manage firewalls and ports and stuff like you might need to on AWS or something. Maybe instead of maybe I should say you don't get to, instead of you don't have to, because it is true that the Internet Computer doesn't have low-level networking like TCP/IP, so that is probably a disadvantage. A built-in sandboxing, like you have the WASM sandbox, you have like an OS sandbox, like just there's a lot of security automatically built in. You have access to threshold protocols, so you can actually sign, like you can create Bitcoin key pairs and Ethereum key pairs, where the key pair is never stored on any one machine. And you can actually sign a Bitcoin and Ethereum transactions from the Internet Computer. You can, I'm not sure why we put verifiable source code, but let's go see. Basically, on the Internet Computer, you compile everything down to WASM and you deploy that WASM logic to the Internet Computer. The Internet Computer will give you a hash of the WASM. So basically what you can do is you can take source code, compile it down to WASM, go to the Internet Computer, ask for a WASM hash, and check that those hashes are the same. Then you can basically know that the source code you're looking at is a source code that's on the Internet Computer. So I guess that's what we mean by verifiable source code. And then blockchain integration. The Internet Computer has a very nice tight integration with Bitcoin right now. And that not only can you create Bitcoin key pairs, sign Bitcoin transactions, you can also read from the Bitcoin UTXO set, and you can actually send Bitcoin transactions directly to the Bitcoin blockchain from the Internet Computer, which I think is pretty awesome. And then just the developer experience. Like in many ways, the Internet Computer is, I think, trying to just have a very, very nice developer experience where it's building in, load balancers and port management and all kinds of stuff, so that you just write your logic and move forward. And orthogonal persistence is a concept we'll discuss today, where basically you write a variable to memory and it just stays, which is really cool. Now, some drawbacks. Azle is beta software. There could be security issues. Right now, it is more expensive, significantly so, than Rust or Motoko. And I don't think we have missing APIs anymore. Is this out of date? Oh, I see what it's saying. Yeah. So, Azle is not Node.js, right? It's you're not going to have every API that you might have on Node.js available to you, and there could be some JavaScript features that are missing. Luckily, we are in the middle of completely upgrading Azle to a totally new JavaScript engine, and it's going to solve quite a few of these problems. It'll be way less expensive, hopefully, and we'll be able to plug more APIs, and there should be very few missing JavaScript features, and the security will improve, and we will get closer and closer to getting out of beta, which will be nice. And then the Internet Computer itself does have some problems. Just like Azle, the Internet Computer is very early. It's been launched for over 2 years, so 2 years is a long time, but relative to Ethereum or Bitcoin, it's relatively short. You'll notice that there are high latencies when you do network requests into canisters or do calls between canisters or between applications. The latency can really build up. So you're talking about on the order of seconds, 2 to 10 seconds, depending on the type of request that you're doing. And sometimes it just might not be appropriate for your application. Also, the amount of computation that you have available to you is limited and expensive relative to an EC2 instance, because everything's replicated, because it must be deterministic and it goes through consensus. There's just certain computational limits that you might reach, and it's going to be more expensive because you have to pay for that. There's actual computers running. It is limited in scalability. You're not going to be deploying a Twitter to the Internet Computer anytime soon. For prototyping or small applications, or it just really depends. You need to think deeply about your application and think deeply about the properties that you want from your application to decide if the Internet Computer is appropriate for you. A lack of privacy. All data that you store on the Internet Computer is, by default, node operators, those that are running the actual nodes software, they can see the data running. So relative to AWS or something, you probably have worse privacy. But if we compare the Internet Computer to Ethereum or Bitcoin, which have basically no privacy whatsoever, the Internet Computer is in a nice middle place. Not everyone in the world can see the information in your application, but more people than just AWS or your company could possibly see it. So it's kind of a little middle ground. Dfinity, the foundation behind the Internet Computer, is working on general purpose private or confidential computing. It's probably a moonshot, it's a very difficult, crazy endeavor, but hopefully that will come in the future. And then NNS risk, we haven't talked about this much, but the NNS is basically a DAO, a decentralized organization that controls the Internet Computer Protocol. Anyone who owns ICP can be part of this DAO. So I'm part of this DAO. I actually do participate in voting. The problem, though, is that Dfinity, the foundation that created the protocol, a lot of ICP follows Dfinity. So it is a liquid democracy system. So you can follow other ICP holders to give them your vote, basically. A lot of people follow Dfinity, which gives them the ability to basically write to the protocol whenever they want. Now, it's very transparent. You can see the proposals, you can see votes and everything, but that is a risk, right? If the NNS is too centralized for your liking, you just need to keep that in mind. So, and it's not necessarily set in stone, and there's hopefully lots we can do in the future to fix this, but it's definitely a risk to keep in mind. So yeah, you can dive into this chapter and come to conclusions for yourselves. Let me jump. I think I'm going to jump to chapter 7 because it talks about this overview type of stuff. So chapter 7 is just an overview of the internet computer. We already talked about it, like I said yesterday, a lot, but let's just go into the structure of the network a little bit. It's a decentralized cloud platform. I like to say it's progressively decentralizing, right? Its full vision is not here yet. This is not perfect software. And the main point is to be owned and controlled by independent entities around the world. I think we talked about that. And real quick, let's just discuss how the whole network is partitioned into sub-networks, right? So you have the whole network that is the internet computer. You split it up into sub-networks. They're all running the same consensus protocol. And the important thing here is to know that there are between 13 and 40 nodes in each of these sub-networks. They're all coming to consensus. They're all communicating with each other with a BLS signature scheme called chain key. And how do you interact with these canisters? We haven't talked about that much, but basically what you do is you make HTTP requests into the canister. And there are libraries that make that very simple, or you can do the raw HTTP if you want to, but that's basically how you do it. And by the way, you can check out this cool dashboard, dashboard.internetcomputer.org. These are the subnets. You can go take a look at all those. And then the dashboard itself, you can see, the nodes all over the world and a bunch of stuff that's happening. So really cool resource in my opinion. Now, what we haven't really talked about are canisters. And I'll use this word a lot from now on. A canister is just an internet computer application. So imagine your code, your binary, and the state or the actual, the data, the variables, and everything. That is your canister. That is your application. And basically, it's just a WASM module, right? It all compiles into WASM, gets deployed, and that WASM has access to memory. Each canister has a 4 gigabyte heap. So all the global variables, 4 gigabytes is your limit. And you have a 64 gigabyte storage that we call stable memory, which we'll talk more about, not today, but in other lessons. And yeah, that's basically it, right? Canister has your code, has your state. You have 4 gigabytes of heap. You have 64 gigabytes of stable storage. All state changes, anything that changes in your canister, anytime you update variables or whatever, these changes go through the process of consensus. And consensus is, excuse me, is basically the Byzantine fault tolerant protocol that provides Byzantine fault tolerance. And it does take a few seconds for this to happen. And we expose canister functionality through methods. And we'll talk about the different types of canister methods today. And like I said, these methods can be invoked through HTTP. And there are 2 types of methods, which we'll get into: query methods, which are read-only, and update methods, which are read-write. So that is a canister. That is the internet computer in a nutshell. Before I move on, let me pause here for any questions, and then we'll move on to chapter 3, installation.
I'm curious why WASM was chosen.
I did not invent the protocol, so I don't know exactly why DFINITY chose WASM, but other blockchains have chosen WASM as well. And so WASM is basically, it's a portable and efficient bytecode, or also known as an instruction set architecture, for a virtual machine, a WebAssembly virtual machine. And so it's kind of like imagine every CPU has an instruction set architecture, right? It has a language that it can read, and you basically compile your programs down into a binary format that represents that language. So Intel, lots of machines run Intel processors, which will most likely run the x86 bytecode, and there are ARM processors that run the ARM bytecode. There are RISC-V processors that run the RISC-V bytecode. Ethereum has its own virtual machine called the Ethereum Virtual Machine, which will run Ethereum Virtual Machine bytecode, EVM bytecode. And Bitcoin doesn't really run programs, but it also does have opcodes and I guess a simple form of a bytecode as well. So that's what WASM is, right? It's a bytecode just like all these other things, but it's a general purpose bytecode that was to map to allow you to compile like C and Rust and low-level languages into it and have it run at near native speeds. And WASM came out of a thing called ASM.js, and the idea was, can we make a bytecode format that you could compile Rust and C and stuff into and get like super awesome performance in the web? That was one of the motivating factors. Well, it turns out, and this was known from the beginning, I'm pretty sure, WebAssembly is not designed just for the web. It's actually quite self-contained. It does not need to run in the web. It can run outside of the web. It can run on servers. And various blockchains have chosen WebAssembly as their core virtual machine. Why would they do this? Well, for one, it seems like it's becoming a universal compilation target. All the browsers have it implemented. Various like cloud companies are using it outside of the browser. I mean, at least I feel like I can think of at least 2 or 3 that are doing this. So yeah, it's starting to be used inside the browser and outside the browser. It's very efficient. You can compile low-level languages into it, and you can, I think, from my understanding, you can make WASM bytecode deterministic very easily, and determinism is key for replicated computation. So I feel like it's just like, it's an open standard. It's well supported, well implemented. I think it even has formal verification, meaning like, mathematical proofs stating certain things about its correctness and such. And it's easy to integrate into a blockchain. So Ethereum itself was experimenting a few years ago with swapping out the Ethereum virtual machine for a WebAssembly version for various reasons that I don't know everything. I don't know all the reasons why, but they so far have abandoned that project. But you'll see like Ethereum layer 2s, like tons of blockchains are probably going to choose WASM. Arbitrum, one of the biggest Ethereum layer 2s, has a project called Stylus, which I believe is WASM at its core. Cosmos has a project called Cosm WASM. And like, yeah, WASM is just proliferating everywhere. So hopefully, I mean, I don't know exactly why, but hopefully that gives you some idea.
Yeah, thank you. That's very interesting. Especially, I had no idea that it ran outside of the browser too, and why it runs outside the browser. So that's interesting.
Yeah, you can. Yep. For example, there's a project called WASX by Wasmer. Wasmer is one of the main WebAssembly virtual machines, and they actually have compiled. You can like compile CPython into WASM and just run it basically. So yeah, it's becoming quite the compilation target, which is pretty cool. I actually have well, this has nothing to do with what we're doing, but I think it's cool. This is a project that I made with a friend called WASM Metal, and the idea is to actually make a WebAssembly CPU, like a physical processor that will execute WebAssembly bytecode. So we didn't do that much with it, but we started to kind of, from our college knowledge of microarchitecture, started to put together like an actual physical CPU. So if you're interested, go check it out. It has like 300 stars, but there's literally nothing in the repo. So I think people just think the idea is cool. So anyways, any more questions? Okay, if there are no more questions, then we will dive into actual programming, or at least getting ready to program. So chapter 3, these are the prerequisites for getting started with Azle. You basically need 2 things. You need Node.js 18. If you're new to Node, please do not install Node from like node.js.org. Just use the Node version manager. Just run this script or go to the GitHub repo for Node version manager. It makes it so easy. It doesn't mess with your permissions. You don't need to be sudo, and you can switch between versions and delete versions really, really easily. I've used this for years. It makes it so easy, like to install on a Raspberry Pi or on your machine. Or one time at the university, I logged into a machine. I needed Node real quick. I was able to install it with this without changing any permissions or needing root permissions, and do my thing and then uninstall. So highly recommend it. Please have 18 or up. And then you need the, I guess, the Dfinity command line tools. It's called DFX.
Jordan, sorry, if you can share your screen, because I think this information...
Oh, am I not?
No, you are not sharing now the screen.
Was I not sharing the whole time?
Yes, now you are sharing.
I think we had a Zoom hiccup.
Oh, okay. Okay, well, I don't know what you did and did not see, but I'm here in chapter 3 of the book. Yeah, that's where we are. So I talked about Node.js, talked about Node Version Manager. You can go look at the Node Version Manager repo. That's the link. And then DFX, you install it just with this very simple command. Please use version 0.14.2. You can use newer versions if you want, but these are the versions we're testing against at the moment. And yeah, once you have these two tools installed, you're good to go. So you'll just check, do I have Node version 18? Yep. And do I have DFX 0.14.2? Yes. Great. Then we move on to the hello world. If you want to get started super duper fast, you'll just run npx azle new hello world, and this will generate an entire repo for you. So yeah, let's just do that. Oops. Okay. I'm just afraid I already have one, so. Oh, I don't. Okay, here we go. Nice. So that did generate a hello world for me. We'll open up Visual Studio Code. Close all these crazy tabs. Okay, so it generated this project. I want you to focus on how simple this is. There's nothing crazy here. Most of this is what you're already used to. There's a tsconfig.json. Any Typescript project is going to have this, basically. These are the settings we recommend or require. So you can just copy paste this amongst all your projects. There's a package.json. You don't even need any of these scripts. Those are just convenient scripts. All you need is Azle. So let's npm install. It's going to install Azle for us, and it's going to generate a package lock.json as well. Perfect. And then we have a git ignore. It's just going to ignore any of the generated, directories and things that we don't need. The first new thing that we see here is the dfx.json. This is a configuration file for the internet computer. It tells DFX basically about all of your canisters. You can have a lot of canisters if you want. In this case, we have one canister called Hello World. And for now, you just copy paste this configuration. We're trying to get this to be way simpler. So in the future, it'll look like this. Type Azle main. Like that's what we want it to be at. But for now we're stuck with this. If you want to add more canisters, you would just, copy paste it, change the name. Okay, cool. Now you have 2 canisters. So nothing crazy. And that's, again, just a configuration file for DFX so that you can deploy locally or in production. Then we come to the application itself. Here we are. First, notice that we have the Azle library here. That's where we're going to be importing most of our stuff from. And we're starting with 2 imports, query and update. These are absolutely fundamental. Before we do that, though, I want to start the deploy process. So to deploy, the first thing we're going to do is run a local internet computer replica. To do that, we're going to use the DFX commands, and we're going to run start. Okay, now I have a local replica running. Basically, this is a local internet computer node on my machine. And I'll open a new terminal to deploy. I'm just going to run DFX deploy. DFX deploy is going to take my application, do a bunch of under the hood compilation stuff to basically get it into WASM, and then it's going to upload the application to my local replica. So we'll let that run. The first time you do this, it's going to take a few minutes, like 5 to 10 minutes. So don't necessarily worry if it takes that long. Once you've installed it the first time, generally speaking, every time thereafter will be much faster like this. And we are working on a new version of Azle, like I said, that, I mean, I'm hoping to, in the end, I'm hoping to get the compilation down to like under a second and even have hot module swapping. We just don't have it yet. So, okay, so this has been deployed and you can interact with it in 2 ways. One is to interact through the browser and one is through the command line, but we'll get to that in a second. First, let me show you what this application is actually doing. We import query and update. We call these annotations. So we kind of made the syntax up so that we, because TypeScript and JavaScript don't have decorators on functions, which is really sad. So we created this thing called an annotation. Basically what you do is if you want to expose read-only functionality that responds very quickly, tens to hundreds of milliseconds, and doesn't go through blockchain consensus, then you mark your function as a query function. So get message is, all it's going to do is, boom, read this from the heap and return it. Super fast. Does not go through consensus. If you want something to go through consensus, and if you want your change to actually persist, then you mark your function as an update function. So here we would receive a message, and we'd set the global variable message to whatever new message is. And then, very importantly, this is called orthogonal persistence. This will stay between update calls. So let me show you how that works. Yeah, get message has nothing in it. It's just an empty string. But if we set the message to hello world, there we go. Boom, hello world is there. Notice, it's just persistent. Like this variable is just here. The internet computer will ensure that your canister continues to run until you run out of something called cycles. We haven't talked about cycles yet, but all computation on the internet computer must be paid for. And you pay for it by using the native token called ICP. You convert ICP into cycles, and you send those cycles into your canister. So all canisters have a cycle balance. And your cycle balance is going to go down over time as you use network resources and as you use storage and as you use computation. So the internet computer is going to make sure that your canister continues to run as long as you have cycles. And your heap, so this message will just stay there as long as you have cycles. Or if you decide to update the code of your canister, in that case, your heap is going to be wiped. So you'll lose all your heap information every time you deploy a new version. But if you don't deploy a new version, your heap will simply stay there. And that's what's happening here, right? Hello world is just staying. And then change it. Now it's changed. Okay, so yeah, that's query and update. I mean, chapter 4 is, if you want to, it just goes in and explains each of these sections, basically like what we just did. Shows you how to start your replica, shows you how to deploy, shows you how to interact with your canister. So we interacted with it from this UI, which is nice. You can also interact with it from the command line. You say DFX canister call, put the name of your canister in, and then put the method that you want to call. Yep. And then if you want to set the message, I'd say set message, and I'd pass in my parameters. Changing it again. Oops. And now it says changing it again. So, command line or the browser, whichever one you want. Chapter 5 is all about going a little more in depth with deployment.
Sorry, Jordan, we have a question from Theo.
Yes, sure.
Jordan, just a quick question about orthogonal persistence. Is that synonymous with session storage?
It depends on what you mean by session storage. For example, session storage is a very specific API in web browsers. So it is not web browser session storage. If you're talking about server-side session storage, no. I mean, basically, no. It is not the same concept. Orthogonal persistence is the fact that the heap, like the WebAssembly memory pages, the actual memory where that heap is stored, is persisted for you automatically, and you don't have to do anything. That is a concept that I've not seen implemented anywhere else in any programming environment that I've ever used. So I think it is quite unique.
Okay, great. And also, quick question. I got up to the point of installing everything and having the Typescript file, but I could not get it to start using DFX start. And I'm not sure what I'm missing here.
Okay. Could you real quick tell me what the error says? It might be a quick fix.
It just says bash DFX command not found when I do DFX start.
Okay, so you might just need to do this. Did you try that?
Okay, I haven't tried that. I'll try that.
That's probably the problem.
Okay.
But yeah, if you have any problems, you can always DM me. My handle is LatsonJets on Twitter or Telegram, or I think Discord is LatsonJets now, maybe too. I'm not sure. So if you need to get hold of me, you can. Okay, so yeah, chapter 5 is all about deployment, DFX start, DFX stop. If you have some errors, you can do stuff. Blah blah blah. It talks about interacting from the command line, like we just did. Gives you a few more commands. Talks about the web UI like we just did. Also, if you're going to build like a web application, like a front end, you're going to need to use an agent. An agent is basically the client-side library for interacting with your canister. @definity/agent is the npm or is the JavaScript one. So if you're making a web app, that's what you'll use. There's also a Java agent, there's a Python agent, there's a Rust agent, so it just depends on what language you're using. But basically, an agent is the client-side library that makes it really easy for you to interact with your canisters. So you're definitely going to want to use an agent unless you're going super rogue and want to do your own raw HTTP requests. That probably won't end well, but you can do it. Or if you're making like a REST API, that's a little different story as well, and we'll talk about that not today, but in the future. And then, yeah, deploying to mainnet. So once you've tested locally and everything and you're ready to deploy to the actual internet computer, you need to go get cycles somehow, right? And you can look at the official documentation or maybe talk to ICP.Hub or people about, the cycles. There's a cycles faucet that I guess gives you, a little bit of cycles to get going. But also, it's not that hard to just buy ICP off of Coinbase or something. Just you don't need that much to get going. And what's cool is you just change the network to IC, and then you just hit deploy, and it's basically the same thing as local. So that's pretty cool. Chapter 6 is all about the examples again. Remember, there's like 60 examples, so don't forget to search through these if you need help. And we already talked about Chapter 7 and Chapter 8. Chapter 9 we also already talked about, which would be query methods, but maybe we can go into a little bit more depth. If you have forgotten, this is a query method. It's read-only, right? And to go a little bit more in depth, why are they so fast? Well, because they don't go through consensus. They come actually back from a single node. So like you're asking only one node out of the 13 to 40 to tell you what's there. And there is a 5 billion WASM instruction limit. So that's like, I don't know, maybe 1 second worth of computation-ish based on like a 3 to 5 gigahertz CPU, assuming instructions are analogous to CPU cycles, which probably aren't, but probably a good rough estimate. You have 4 gigabytes of heap. So you can actually do, so notice in the update, we're actually writing into the global variable. I mean, you could do that in the query method as well. You could write to here, you could, make all kinds of other variables and write to them and stuff. But the system will just discard that after the fact. So it's just like, oh, cool, you wrote to this, great. And it'll just throw it away as soon as the call's done. And this is an old figure. It's hard to get these figures, but I think a good rough estimate is that each canister could probably handle up to 32,000 queries per second. So if you're trying to think of like how to scale your app, just think, well, one canister, 32,000 queries per second. And yeah, here's an example of if you do have like a little database, just key value store, you could definitely write to it in your query, but it's going to disappear after the fact. And there is an instruction limit of 5 billion instructions, like we talked about. Here's an example of something. It's like building a pyramid of asterisks. Once you have too many asterisks, it's just too much, and you'll hit an instruction limit. Just not fun, but it happens. So any questions about query methods and being read-only and this basic concept? Very important concept to understand. Okay, and then we'll just go over chapter 10 here. We saw the update method, right? We talked about this 1,000 times, but let's just go in here. It's read-write. It's actually going to be executed on many nodes, if not all the nodes in the subnet that you're in. It does go through consensus. Latency is going to be, 2 to 5 seconds. Between canisters in the same subnet, probably the same. Between canisters in different subnets, probably double that. You have a 20 billion WASM instruction limit. So we could talk more about the instruction limit real quick. This is just an unfortunate consequence of a decentralized computer for the moment. We have to limit the computation, apparently. So an instruction is talking about a WebAssembly instruction, right? So, at the very fundamental level, you have, at the opcode level, you're going to have instructions. I don't know if an instruction is one opcode or not, but you can think of it as like CPU cycles or something similar to that, but it's like the most fundamental unit of computation. An update message, once you go beyond 20 billion of these things, then it's over. It's just cut. And same thing in a query message, once you go over 5 billion of these things, it's just over. It's cut. If you ever want to see how many instructions you're using, you can import the IC object right here. And you can get a snapshot of current instruction usage by calling the instruction counter. This will tell you how many instructions have been used up to this point. So, FYI. And yeah, so far we're only talking about updates and queries, so you got 20 and 5 billion. You have a 4 gigabyte heap, just like with query methods, but anything you write there will actually stay. You have this needs to be updated. It's a 64 gigabyte stable memory limit, not a 48 gigabyte stable memory limit. And again, anything you write into the stable memory section, which we'll get to in chapter 12, I think, the next couple days, more or less. And then a good rule of thumb is probably around 900 updates per second per canister. So 32,000 queries per second for reading. Writing is way heavier. So, around 1,000 update calls per second per canister is what you're looking at with update methods. So that will just help you figure out how to scale, because if you need to scale, you basically need to add more canisters for the moment. And here are some examples of simple update methods. Incrementing a counter, our little message database. Here's an actual database. It's a little more advanced than the message database because it does have keys. So you can get a value here by just reading the value from the database. And you can set a value by just writing into the database. Nothing crazy. And we will talk about stable stuff later, but if you want to write into that 64 gigabyte area, and if you want to make sure that your data doesn't get wiped every time you update your code, then you can use a stable B-tree map. And it has very similar methods to other maps. Get, set, get, insert, whatever, same thing. And then, here's what's cool. If you ever throw an error, basically, in WebAssembly, it's called a trap. If your code traps, then everything that has happened in that update call up to that point automatically gets deleted. So you actually have atomicity within update calls, which is really cool. There's some nuance to that later when we talk about cross-canister calls, but in a synchronous update call, it's either all going to happen and be committed or not. And you get that for free by default, which is really, really nice. And here's just an example of a simple database, and then basically how many entries you could write into this before you hit the instruction limit. And if you call this with 100,000 entries, it's going to fail. So 20 billion instruction limit in this case. So that's all we have planned to cover today. So I am happy to answer any questions you might have.
Jordan, I have one question. I'm pretty much stuck in the current web computer paradigm, and I'm just trying to think about what kind of applications get developed here. Can you kind of orient me on that, or just talk about that?
Yeah, sure. Were you here yesterday?
No, I wasn't. Sorry.
Okay, you should. Once these are uploaded to YouTube, you should watch yesterday's video. We basically went from the beginning of blockchain history to where we are today, and then we talked a lot about it. So happy to talk about it here as well, but just wanted to let you know about that. So basically with decentralized computation, it gives you, it removes central points of failure, right? So for example, think of the Twitter API, or a Twitter API, or an X API, or a Facebook API, or whatever. Imagine you want to build a business on top of this API that's completely owned and controlled by another company. And you go and raise funds to build your business on top of that company, on top of that company's API. Well, you are completely at the whim of the company that owns the API, right? And if they decide to shut down your access or charge outrageous amounts or whatever, for whatever reason, you really don't have any recourse. And this has happened multiple times in the past. I think some notable examples are Zynga. I think this is pretty common knowledge that Facebook and Twitter have done this to developers in the past. where they've taken away the API. So this is one example of something that a decentralized cloud would provide. It would provide you a way to build a credibly neutral API, one that is not owned or controlled by any one entity, but one that is democratically controlled, or even controlled by no one. For example, on Ethereum, smart contracts aren't controlled by anybody in some cases. Like the Uniswap smart contract is basically a decentralized exchange. It's very similar to Coinbase or Binance, but no one's running it. It just runs itself, and people just pay themselves to use it. On some days, it has more volume than Coinbase itself has. That's crazy. And yeah, Uniswap is not going to be discriminating against people for any reason, right? Uniswap, like the actual core smart contract, it can't see ethnicity, it can't see politics, it can't see religion, it can't see how tall or short you are. It doesn't know what programming languages you use. Like, it's just going to execute. So I think credible neutrality and removing platform risk is just one reason you would want to use a decentralized computer. And I mean, these benefits, I think there's many different angles to look at them from, but basically decentralized computers are the absolute most secure computers that you could possibly create. They remove intermediaries. They remove the temptation for humans to misuse and abuse power. For example, the Bitcoin network, it's hundreds of billions of dollars worth of value. No one can just decide to increase the supply of Bitcoin or decrease the supply of Bitcoin or do anything with Bitcoin, which is a little sad because Bitcoin doesn't really progress much. But it is an extremely resilient system for what it is. You have to go get you have to convince many different people from many walks of life doing many different things to come together to actually change it. And that is a powerful property that simply does not exist on any centralized cloud platform. So I would just start to think deeply about, like, what does it mean for a group to own a piece of software? What does it mean for no one to own a piece of software? And how would that change how that software works? And I think that's a lot of what Bitcoin, Ethereum, DAOs, and the whole blockchain space, they're showing us what can be done. And obviously there's scams and silly, ridiculous things, just like, the internet has always had that. The internet wasn't that cool in the 90s, but now it is absolutely essential to everything that we're doing. So does that help? Yeah.
Yeah, that's helpful. I'll take a look at the video also. Can you talk a little bit, earlier you mentioned something about identity management. I know that's going to be hugely important if it isn't now, especially going forward. What's that about on ICP or on Azle?
Yeah, so I can show you real quick the basic authentication mechanism of the internet computer. So basically, what happens on the internet computer is when you interact with the internet computer, you interact using a public-private key pair. So your agent will help you generate these key pairs. And you sign messages, you sign your HTTP request essentially with the key pair. Then once the internet computer calls a method, you have access to the public key by calling IT.caller. IT.caller returns something called a principal. A principal is essentially the address, the public identifier of the key pair that made the call. So using IC.caller, you can implement all kinds of authorization based on that. So that's like the most basic mechanism, and that the internet computer enforces for you automatically. To build and to get this all to work nicely, there's a few ways to do this. Like, you can imagine just a MetaMask snap working, like a snap built for the internet computer working to do this. But probably the most popular solution right now is something called Internet Identity. Let's see. No, that's the main website. Internet Identity. Yeah. I would recommend going to the official internetcomputer.org documentation and learning about internet identity from here. Unfortunately, the internet computer documentation, I feel like sometimes they don't explain things like as they are, so you might have to read through some marketing language and stuff, unfortunately. But there is a whole ton of information on internetcomputer.org, and internet identity is one of the solutions that a lot of people are using. So internet identity will essentially take care of your key pairs for you, so that you can like use biometric, WebAuthn, YubiKey type stuff, and then it creates session key pairs. And this is all abstracted away from you, and it's very easy to implement on the front end. And once you have an identity, it can automatically sign every request for you, and then you just use IC.caller on the back end to do your authorization rules. So hopefully that answers that question.
Yeah, thank you.
Yep.
Also, I see familiar faces here: Ephraim, Negar, Sarah, Simran, Taha, Umut. Yeah, please, if you have some questions, don't be shy. It's the moment to ask, please. Thank you.
Yes, Theo.
Jordan, I just am still receiving an error for deployment. I'm seeing a DFX installation. It's saying unrecognized OS type. I think there's.
Yeah. What OS are you using?
It's saying Ming Windows 64.
Yeah, so you cannot use Windows. So
Okay. So
you need to. You can use Windows. You just need to use Windows subsystem for Linux.
Oh, I see.
So
okay.
Yeah, notice right here. I should have said this. You should be using a Nix environment, Linux, macOS, or WSL if using Windows.
Oh, that's an installation. Okay, gotcha. Thanks.
Yeah, WSL is super easy to use nowadays, so that should work for you.
Thanks, Ruben.
Yep. Okay, well, if there are no more questions, then I'd say that is the lesson for today. We basically covered chapters 1 through 10 is what we did, and we'll start with chapter 11 in the next episode.
Thank you so much, Jordan. Yeah, the next episode will be this Thursday. Again, same time, 6 p.m. PST. Yes, also we have the Discord channels, the Demergent Lab Discord channel, ICP.Hub North America Discord channel. If you have any question meanwhile, please feel free to reach out to Jordan, Ritvik, Chetan, or other engineers. They are so happy to reply you. Yeah, thank you again, Jordan, for your time, for your explanations. We will post the YouTube, the first lesson yesterday in an hour in the YouTube channel, and also this session will be posted as well tomorrow. Thank you so much, and everybody. Yeah, have a good night.
See you. Good night.
See you.
See you guys.
Bye.
Thank you. Good night.